When something travels between the stars and enters our solar system, we expect it to follow certain rules. Gravity dictates the path, the sun's pull determines the trajectory, and then there's 3I Atlas, an object that appears to be rewriting those rules in real time. Right now, as we speak in early January 2026, this interstellar visitor is making its way through the outer reaches of our solar system. It's been roughly 8,000 years since 3I Atlas entered the Oort cloud, that vast spherical shell of icy objects at approximately 100,000 astronomical units from the Sun. That's 15 trillion kilometers from our star, a distance so vast that light itself takes more than a year and a half to traverse it. For those 8,000 years, 3I Atlas has been falling toward the Sun, but now it has reached the turning point, embarking on the second half of its journey, heading back out into the cosmic void. This is where things get interesting, and if you want to follow this story as it unfolds over the next few months, I'd recommend hitting that subscribe button because what happens next might fundamentally change how we think about visitors from beyond our solar system. Let's look closer at the data, because there's something deeply unusual about 3I Atlas. When astronomers track objects in space, they use sophisticated mathematical models based on gravitational physics. These models are extraordinarily precise. We can predict where a comet will be years in advance. The math works. It always has. Except with 3I Atlas, it doesn't quite work. The object exhibits what scientists call non-gravitational acceleration. Something else is providing an extra push, nudging it off the path that pure gravitational dynamics would predict. Non-gravitational acceleration isn't entirely unprecedented. When comets approach the Sun, ice sublimates into gas and jets outward, creating a rocket effect. But 3I Atlas has traveled so far from the Sun through regions so cold that this explanation becomes difficult to justify. Out in the Oort cloud, temperatures hover just above absolute zero. Ice doesn't sublimate vigorously enough under these conditions to produce measurable acceleration. Here is the crucial detail. The non-gravitational acceleration of 3I Atlas has been persistent enough that it must be included in any forecast of where the object will be. This isn't a minor correction. Without accounting for this mysterious push, our predictions would be off by millions of kilometers. So, what does this actually mean? We're watching an object that behaves unlike the comets we know. Either our understanding of outgassing and extreme cold is incomplete, or we're dealing with something that doesn't fit into our existing categories. The designation 3I stands for Third Interstellar Object. The first was Oumuamua in 2017. The second was 2I Borisov in 2019. But where 2I Borisov acted like a conventional comet with a visible tail and predictable behavior, 3I Atlas has been different from the start. The object was detected by the Atlas Survey System, a network of telescopes scanning for potentially hazardous asteroids. When astronomers calculated its orbit, they immediately recognized the hyperbolic trajectory, the signature of an object not bound to our Sun. The excitement was immediate. Here was another messenger from interstellar space. But as observations accumulated, that non-gravitational acceleration kept showing up. It wasn't measurement error. It was real, persistent, and unexplained. And now, as 3I Atlas heads back toward the outer solar system, it's not drifting into obscurity. It's heading toward an appointment with Jupiter. Building on this unusual acceleration pattern, let's talk about what's going to happen on March 16, 2026. That's just over 2 months from now, and the date has been circled on calendars at NASA, ESA, and observatories worldwide. On that day, 3I Atlas will pass within 53.61 million kilometers of Jupiter. That's about 140 times the Earth-Moon distance. In everyday terms, it's vast, but in planetary dynamics, this is extraordinarily close. Let's look closer at the data because there's a number that should make everyone sit up. Jupiter has what astronomers call a Hill sphere, the region where the planet's gravity dominates over the Sun's tidal forces. For Jupiter, this Hill radius extends to approximately 53.5 million kilometers from the planet's center. Now compare that to 3I Atlas's closest approach. 53.61 million kilometers. The interstellar object will pass just 110,000 kilometers beyond Jupiter's Hill radius. That's a difference of roughly 0.2%. 3I Atlas is threading a needle, skating along the edge of Jupiter's gravitational dominance. This is not how random encounters work. When an object comes from interstellar space on a hyperbolic trajectory, the odds of passing this close to any particular planet are vanishingly small. Yet here, we have 3I Atlas, with its unexplained acceleration arriving at Jupiter's doorstep with Swiss watch precision. But there's more. On March 17, 2026, 3I Atlas will pass within 30.46 million kilometers of a small moon called Eupheme. It's one of Jupiter's irregular satellites discovered in 2003, just 2 kilometers across. This is a tiny captured rock, one of 95 known moons orbiting Jupiter. So, why care about one obscure moon among dozens? The answer lies in the timing. Eupheme is part of the Ananke group, a family of 15 moons on highly elliptical orbits circling Jupiter opposite to the planet's rotation. These are captured objects, shattered remnants of larger bodies that Jupiter ensnared long ago. Eupheme's orbit takes 588 days to complete. Because it's so elliptical, the Moon's distance from Jupiter varies dramatically. At its farthest point, Eupheme reaches 27.7 million kilometers from the planet. Here is the crucial detail. Eupheme will reach its apogee, its farthest point, on January 23, 2026. That's just 15 days from now, and 52 days after that, 3I Atlas will make its closest approach to this moon. When Eupheme is at its farthest point, it's in the most weakly bound part of its orbit at the edge of Jupiter's influence, moving slowly in a configuration where dynamics are most delicate. And that's when 3I Atlas passes nearby. Now let's acknowledge what astronomers would say. There are 95 moons around Jupiter. With that many objects, the probability that one would be in some interesting configuration is not that small. This is the cosmic coincidence defense, but this contradicts what we previously thought about interstellar objects. Oumuamua came and went without close planetary encounters. 2I Borisov also maintained safe distances, but 3I Atlas is different. It's engaging with the solar system in a way previous visitors didn't. That non-gravitational acceleration means its trajectory has been modified by forces we don't fully understand. And now it's arriving at Jupiter at a threshold of gravitational capture dynamics. At closest approach on March 16th, 3I Atlas will be moving at approximately 66 kilometers relative to the planet. That's nearly 240,000 kilometers range. It's fast, but not so fast that gravitational interactions become negligible. Jupiter's gravity will absolutely affect 3I Atlas, bending its trajectory and potentially stressing the object. What kind of dynamics could actually happen? That's what we need to explore next, because the answer involves looking at how Jupiter acquired its family of 95 moons and whether that family is about to get larger. Eupheme was discovered in 2003 by astronomers using the Mauna Kea observatories in Hawaii. With a mean diameter of just 2 km and an albedo of about 0.04, this moon reflects very little sunlight. It's dark, small, and distant, but Eupheme didn't show up alone. It's part of the Ananke group. They all orbit Jupiter retrograde, opposite to the planet's rotation. They all have highly eccentric orbits inclined at steep angles. These are not orderly orbits from moons that formed in place. These are the chaotic orbits of captured objects. The prevailing theory is that the Ananke group formed from the breakup of a single larger parent body. Sometime in the distant past, a wandering asteroid or comet passed too close to Jupiter. The planet's gravity captured it, pulling it into an unstable orbit. Then, through collision or tidal stresses, this parent body shattered. The largest fragment was named Ananke, and the smaller pieces became the 14 other moons, including Eupheme. This strongly indicates they didn't form in place. They were captured. Jupiter is very good at capturing things. This brings us to the physics directly, And this is where the mathematics become uncomfortable, because when you calculate the velocity changes required for capture and compare them to what natural processes can produce, you run into a significant problem. As we established earlier, the relative velocity is 66 km/s. For a fragment of 3I Atlas to become gravitationally bound to Jupiter, it needs to slow down until its speed drops below the local escape velocity. At a distance of 53.61 million kilometers from Jupiter, the escape velocity is approximately 2.2 km/s. Do the math. The fragment needs a velocity change of at least 63.8 km/s in precisely the right direction. Can a natural breakup of a comet produce velocity kicks of 63.8 km/s? The answer, according to physics, is no. For water ice, sublimation kicks are measured in hundreds of meters per second, perhaps up to a kilometer per second at most. That's off by a factor of more than 60. Tidal breakup doesn't fling fragments away at high speed either. It gently pulls them apart. The physics doesn't allow for a natural mechanism that could produce the required change. The required velocity kick is 63.8 km/s, but natural processes max out at a few km/s. Furthermore, the margin for error is tiny. The kick must precisely calibrate the fragment's velocity to something between 0 and 2.22 km/s, a tolerance of about 3%. In engineering terms, this is what we call exquisitely designed. If on March 17, 2026, we observe a new moon around Jupiter that came from 3I Atlas, we'll have observed an outcome that natural physics says shouldn't be possible. That would constitute what some researchers are calling a technological signature. It would suggest that 3I Atlas can control its fragmentation, impart specific velocities, and execute maneuvers that natural physics does not allow. We're not claiming 3I Atlas is artificial, but if we observe these specific outcomes, they would be very difficult to explain using only natural processes. They would require new physics or the consideration of possibilities we've traditionally ruled out. The astronomical community has already begun preparations for what might be the most closely watched planetary encounter in modern history. The most important asset in position is NASA's Juno spacecraft, orbiting Jupiter since 2016. Juno's suite of instruments will be uniquely positioned to observe the event from close range. From Earth, the largest ground-based telescopes, ALMA in Chile, the VLT, Keck, and Subaru in Hawaii, will all be pointed at Jupiter. Optical observations will track position and brightness, spectroscopy will analyze the composition of ejected material, and infrared will search for thermal emissions. The critical observation is this: after March 17th, will there be any new objects in orbit around Jupiter? Discovering a 96th moon would be front-page news, but one appearing immediately after an interstellar object passed through would be extraordinary. Confirming this takes time. We shouldn't expect definitive answers on March 17th, but the data will be public, and amateur astronomers will participate too. For a claim as significant as a technological signature, multiple independent confirmations are essential. This represents a different kind of test for the search for extraterrestrial intelligence. Instead of looking for radio signals from distant stars, we are looking for anomalous behavior during close planetary encounters. We don't need to search a million stars, we just need to watch the objects that come to us. Of course, there's a significant chance nothing unusual will happen. Science is full of mysteries that turn out to have mundane explanations. But the possibility remains that we're about to witness something unprecedented. That's why March 16, 2026 is a date everyone should have marked. As we established, 3I Atlas will be just barely outside Jupiter's Hill radius. It's in a regime where capture is theoretically possible. If the object were to fragment, some pieces could receive velocity kicks that put them into bound orbits. They could become new moons, additions to Jupiter's already extensive family. If you're finding this fascinating, drop a comment below. Let me know, because there's so much more to unpack as we get closer to the encounter date.